So, good morning to one and all. Dear friends, to find out the slope and deflection, there are various methods, and these methods are geometrical method, graphical method, or energy methods. So, as per the question, state the various methods used to find the slope and deflection of the beam. First method is the double integration method, and later on Macaulay's modified this method and we can call as the Macaulay's method, which is suitable for all the type of beams. Second method is the moment area method, in which we can find out the bending moment diagram. That means first we find out the support reaction, then draw the bending moment diagram, and divided by EI, that gives the M by EI diagram. And this M by EI diagram, if we can take the area of that M by EI diagram, that gives the slope. And if we can take the moment of that M by EI diagram with reference to the particular point, we can find out the deflection. Third method is the conjugate method. Conjugate method is the, we can say that the, whatever the bending moment diagram we can draw, this bending moment diagram is considered as a load for the fictitious beam, and this fictitious means the dummy beam, in which if the support is fixed, we have convert in the conjugate beam as a free, and if the end is fixed, free and free to fix. Similarly, for the hinge support, definitely it is treated as a hinge. Roller support, it is considered as a roller support in conjugate beam method. But if there is an internal hinge, then this internal hinge is converted into the roller in case of conjugate beam. And if there is a roller support, internal roller, then it will be converted into the internal hinge. So these are the three methods. Of course, one more method is more popular, that is called as the strain energy method, or it is also called as the unit load method. It is on the basis of principle. First principle, that is we can call as the conjugate beam method, then moment area method, then Macaulay's method, and then Castigliano's force theorem. Okay, and this theorem is applicable for frame as well as beam. So let us start this problem. Here in this problem, we can consider the point load 15 kilonewton W at the free end, and the moment M 50 kilonewton meter at same, that is the at the free end. We know that in case of cantilever, definitely the slope and deflection at A is 0. That means the theta slope at A is equal to 0. Similarly, deflection at A is also equal to 0. But at the same time, when we consider the free end, in case of cantilever, it is maximum. Deflection is also maximum and slope is also maximum. So I can draw the deflected curve. This is the deflected curve. And when we draw the tangent at this point, that means the second degree parabola, we get the theta at B. That is the maximum. And similarly, when we measure this distance, that gives the deflection at B, which is maximum. That means at the fixed end, slope and deflection is 0, but at the free end, slope and deflection will be maximum. This is the beauty of the cantilever beam. So let us start this problem by using the Macaulay's method. In Macaulay's method, we have considered or some limitations, or we can say that some precautions. We can take the section in the last region. So when we consider this beam, here it is observed that the load is only at the fixed end. That's why we have considered only one section. So this section, sorry, this section is taken, just a minute. So for this beam, we have considered the section here at a distance of x meter from the free end. That means in cantilever beam, it is not necessary to find out the support, reaction or moment. We can start from the free end. So let us start. Here we have considered the distance, and what is the moment? Moment at a distance of x is equal to this w multiplied by x. It rotated in the anti-clockwise direction or hogging moment. That's why it is w multiplied by x is the moment due to point load. W is 15 kilonewton and m is equal to 50 kilonewton meter. And the couple is also anti-clockwise. That's why this is also minus. So m, that is 50 kilonewton, multiplied by, here we have considered x, and this x to the power 0. And we know that when we put the power 0 to any variable, its value is 1. And that's why we get the same answer. Minus m into x to the power 0, we get minus m. But from the Macaulay's method, we have considered the role of x to the power 0. That's why we have used mx is equal to w into x minus m multiplied by x to the power 0. Okay, this is the moment. Then apply the Macaulay's method. For Macaulay's method, it is also called as the double integration method. And for this double integration method, this is the equation. Just a minute. So the equation is ei into t2y by dx, ei into t2y by dx square is equal to mx. This is the elastic curve equation, and mx is equal to, we know that, minus 15, that is the value of w, that is minus 15 into x minus 50, that is the value of m, x to the power 0. This is the equation number 1. Now we can integrate this equation with respect to x, as x is a variable, and we know that dy by dx, that use the slope. Therefore, after integrating, we get this equation, that is ei into dy by dx is equal to c1 is the constant of integration minus 15x is after integration, it is x square by 2 minus 50 multiplied by x to the power 0 plus 1. That's why it is 50 into x. Then after application of, we can say that the again integrate. After integration, we get the dy by dx is converted into y, and that's why ei into y is equal to c1 into x plus c2 is the another constant of integration minus 15 x square is converted into x cube by 3 multiplied by 2, that gives the 6 minus 50 into x, so x square divided by 2. After integration, we get this equation. This equation indicates the deflection equation. That is, equation number 2 is related with the slope equation, and equation number 3 is related with the moment equation. And C1 and C2 are the constant of integration. So first we can find out the value of C1 and C2. As we know that in case of the cantilever beam at fixed end, that means when we consider x is equal to L, because we have taken the section from the free end. And therefore, when we consider x is equal to L, that is 3 meter, slope dy by dx is equal to 0. And therefore, when we put this in equation number 2, we get the value of C1. So C1 is equal to 517.50. Similarly, when we put the another apply condition, support condition at x is equal to L, again y, that is the deflection, is 0. We can put this in equation number 3. And so C1 into x, that is 3 meter, plus C2 minus 15 x, that is the 3 to the power 3 by 6 minus 50 into 3 to the power 2 divided by 2, and we can find out the we can say that we can find out the C2, and C2 is equal to minus 1260. Now put this value, C1 is equal to 517.50 and C2 is equal to 1260 with minus sign in equation number 2 and 3, and we get the value of slope and deflection equation. So when we put x is equal to 0, we know that slope is maximum, and therefore when we put x is equal to 0 for cantilever, what happens? This is 0, sorry, equation number 4, this is 0, this is 0, and ei into dy by dx, uh, that is at the theta at support B, ei into theta B is equal to 517.50, and when we divide it by ei, we get the slope. So theta B is equal to 517.50 divided by ei. That means theta is maximum, that is equal to directly C1, right? In case of the cantilever B. Similarly, equation number 5, which is related with the deflection. Again, I have put x is equal to 0 because the deflection as well as slope both will be 0 at the free end in case of cantilever. Therefore, when I put this value again, C1 into x, so x is equal to 0, this will be 0, this will be 0, this will be 0, and we get 1260 divided by ei, that gives the deflection. As minus sign indicate the deflection is downward. So y is equal to, we can see that the C2, and theta is equal to, that is at the maximum, this is equal to C1. Okay, these are the constant of integration, and this directly reflect the slope, maximum slope and deflection of the, we can see that the beam. Okay, so another problem which is related with the conjugate beam. A simply supported beam of span 4 meter as shown in figure. Consider EI is constant. Apply the conjugate beam method and determine the deflection at C, at point C, that is 3 meter from the support A of the given beam. EI is constant. Again, we know that the different methods that we have used to find out the slope and deflection, these are the various deflection methods, slope and deflection method. Now this is the beam. In this beam, step number 1 is to find out the support reaction. And we know that we have three equilibrium equations: summation fx is equal to 0, summation fy is equal to 0, and summation of moment at particular point, say A or D, is equal to 0. And we get the reaction, support reaction, say RA and RD. Here, support A is hinge support, but load is vertical. That's why HA is equal to 0. So there is no issue. So RA is equal to 18.75 and RD is equal to 6.25. This is the step number 1. Step number 2, draw the bending moment diagram. And after drawing the bending moment diagram, we can sketch M by EI diagram. Bending moment diagram divided by EI. In this problem, EI is constant, and that's why bending moment diagram and EI diagram is same just by dividing the EI. So at each support, definitely the moment is 0. At support B, moment is equal to 18.75 multiplied by 1. That's why it is 18.75 divided by EI. Okay. And when we can find out the moment at point C, because we want the deflection at point C, we can say that the RD multiplied by 1 in the clockwise direction, but from the moment is taken from the left to right. So sorry, anti-clockwise direction. So from right to moment is taken from right to left. That's why it is positive. So it is 6.25 into 1. It is 6.25 divided by EI. So this is the positive bending moment diagram. Now in conjugate beam, convert this beam into the, we can see that the conjugate beam. Here the hinge is there at support A, at support B, roller is there. Again, the supports are same. So conjugate beam is the fictitious beam or dummy beam in which reactions are same but in the opposite direction, and this M by EI diagram we can put as a loading diagram for the beam AB. So this is the conjugate beam subjected to the bending moment or M by EI diagram. Then we can find out the moment at point C. So for the moment at point C, it is necessary to find out the reaction at A and at B for the conjugate beam. Again, moment summation Fy is equal to 0. So Ra, Rd is equal to, we can say that the area of this triangle plus area of this triangle. So half base into height. So in this way, we get the summation Fy is equal to 0. Ra plus Rd is equal to 37.50 divided by Ei. This is equation number 1. Similarly, taking moment at point A, so moment of Ra about the same point is equal to 0. Moment of Rd is equal to Rd multiplied by 3 plus 2 plus 1 plus 1, 4. So 4 Rd is equal to, we can say that this area of this triangle multiplied by centroidal distance, CG distance, that gives the moment. In this way, we get the value of Rd. And the value of Rd is equal to 15.625 divided by Ei. Put this value in equation number 1, we get the value of Ra. And the value of Ra is 21.875 divided by Ei. So, deflection at C in the actual beam, original beam, that is equal to moment at C in the conjugate beam. So, moment at C is equal to, we can say that this is the problem. This is the conjugate beam loaded with the M by EI diagram. So, moment, because of this, either we can start from this side or from this side. When we can start from this side, so Ra multiplied by 3 in this direction, then minus area of this half, base is 1 meter, height is 18.75 multiplied by 2 plus from this side 1/3 of 1 plus area of the trapezium, or we have convert this trapezium into triangle and rectangle and the taken the area into CG about the point C. We get the, we can say that we get the moment at C, and moment at C is equal to, we can say that the deflection at C in the actual B. Okay, or we can consider RD multiplied by 1, then area of this triangle, that is half, base is 1 meter into height is 6.25 divided by EI, that gives the moment at C. Okay, we get the same answer. Here generally we are convenient, more uh, suitable to use from left to right. That's why I have show the calculation from left to right. But you can also find out the moment at C from the right to left. And here right to left, we have considered only this triangle and moment due to RD. Okay, so we get the moment at C is equal to 17.375 divided by ER. Okay, so this is the moment. So moment is related with the deflection in the actual beam. So deflection at C in the actual beam, that gives the moment at C in the conjugate beam, which is minus 17. Minus indicate the direction of the deflection is downward. So 17.375 divided by ER. So similarly, in the third problem, this is the third problem. Sketch the free body diagram. Of course, cantilever beam is there. Analyze the beam loaded and supported at each figure and determine the maximum deflection. Again, maximum deflection for the cantilever beam. We know that it is maximum at the free end, that is at point C. Here the value of E and the cross section is given. So we can find out the E multiplied by I. And for moment, again, we know that for the moment of inertia, the value of moment of inertia, it is very simple to find. Here the cross section is rectangular, it is 50 by 75, and that's why the value of I, moment of inertia, is equal to, we know that rectangular section, it is B D cube divided by 12. That's why it is 50 into 75 to the power 3 divided by 12. We can find out the value of I. Then E is known to you, I is known to you. So flexural rigidity, EI, you can find out either in kilonewton per meter square, or kilonewton, or Newton per square. Depending on the requirement, you can convert this. Okay. So here also method is not mentioned, which method we can use or suitable. For cantilever, generally we use the Macaulay's method, that is double integration method, or moment area method, or conjugate beam method. All these methods are suitable. So let us discuss this method. Here it is observed that, as we know that for cantilever, it is not necessary to find out the support reaction. Okay. So first problem is to draw the free body diagram. So for free body diagram, definitely we can show the reaction component. So here at support A, definitely there is a vertical reaction, that is RA. Horizontal reaction is 0 because the load is vertical. Therefore, this HA is 0. No need to show. And third is the moment at A because of the fixity moment at A. Now, this is the free body diagram. Okay. So, for this beam, what is the bending moment? The bending moment at C is equal to 0, because when we start from the moment at C, 6 kilonewton multiplied by 0, it is 0. That's why it is 0. And from moment at B is equal to 6 kilonewton multiplied by this distance 2, that is 12. So this is 12 kilonewton meter is the straight line moment diagram. This is the bending moment diagram, which is straight line. Then moment at A is equal to 6 kilonewton multiplied by 4. Perpendicular distance is 4. Then UDL, that is 4 kilonewton acting over 2 meters. So 4 multiplied by 2 into CG of this rectangular UDL, that is the 2 by 2. So it is 8 kilonewton meter. But this is the parabola. So this is the bending moment diagram. This is the bending moment diagram, partly partly triangular and partly parabolic. Then convert this diagram into M by EI diagram. So this is the M by EI diagram. In this problem, the value of EI is different. The value of EI for the first B to C is EI, and A to B, it's 2 EI, and that's why moment at C is equal to 0. There is no issue. So 0 divided by EI. At B, it is 12 kilonewton meter. At B, just right, it is 12 kilonewton divided by EI. But at B, just left, when we shift toward the B or toward the A, there is a 2 EI. That's why 12 divided by 2, it is 6 divided by EI. So it will be reduced. Then parabola, and this end A, that is the 32 divided by 2, it is 16 kilonewton divided by EI. This is the M by EI diagram. Okay, so this is M by EI diagram. So this M by EI diagram is used to find out the slope and deflection using the moment area method. As I told you, You can use for cantilever beam, you can use moment, uh, we can say Macaulay's method, that is the double integration method, or moment area method, or conjugate beam method. Here we can solve this problem by using the moment area method. So maximum deflection occur at the free end, as in case of the cantilever beam, as we have already discussed. That's why delta max is equal to delta deflection at free end, that is C, is equal to moment of M by EI diagram between support A and C about C. That means we can find out the moment between A, that means the tangent drawn at point A, which is fixed, and that's why it is a straight line. And when we draw the tangent at C, it is inclined line. That's why it is the intercept, vertical intercept between the two tangents. And therefore, it is the moment of area of M by EI diagram between A, support A and support C, which is free end, and moment at C. And in this way, we can take the this bending moment diagram or M by EI diagram is divided into three parts. First part is related with the rectangular portion. Height is 6 by EI and the base is equal to 2 meter. Area of this multiplied by CG, that is the 2 by 2. But moment is taken at point C, that's why 2 plus 2 by 2. And then area of this parabola. Again, area of this parabola is considered 2/3 of base multiplied by height. This total height is 16 by EI. This portion is 6, and that's why remaining portion, that means the remaining height of the parabola is 10 by EI. That's why 10 by EI is considered. 2 by EI is into base is 2, and height is equal to 10 by EI. Multiplied by CG, again from this point it is 2, then from the toe point it is 5 by 8. 5 by 8 of the 2. This is minus, of course. Okay. Then third is the area of the triangle. Half base is equal to 2 meter and height is equal to 12 by EI. So, and the with reference to this, again 2/3 of 2, that gives the deflection at C, which is 95.33 divided by EI. Minus sign indicate, we can say that the deflection is in the downward direction. So this is the third problem that we have discussed in detail. Now the last problem, analyze the beam loaded and supported as shown in figure and determine slope and deflection at C. Take E is equal to 200 GPa and I is equal to, here directly I, the value of I, moment of inertia is given 4.5 10 raised to the power 6 mm to the power 4. Here cantilever beam is given, simply supported beam is given, but method is not mentioned. So here moment area method is not suitable, because for moment area method direct deflection cannot be found out. Either we can use the Macaulay's method or we can use the conjugate beam method. So for that, first of all, we can find out the support reaction due to the 12 kilonewton load. This is the step number 1. And summation Fy, that means we have applied the equilibrium equation. Summation Fy is equal to 0 and moment at point A is equal to 0, we get the reaction. So Rd is equal to 9.6 and Ra is equal to 14.14 kilonewton. That is the support reaction at A and D. Now in the again Macaulay's method or conjugate method is more convenient. Okay. So for the Macaulay's method, here the UDL is acting in between B to C, not at the support and not start from the support A or not from the support D. And therefore, when we take the section from the left to right, it is necessary in Macaulay's method, it is necessary to cut the section from the UDL. And that's why we have extend the UDL from C to D, that means the from C to right support D, and whatever the UDL extend, same will be extend from the bottom side, so that the effect is nullified. And therefore, we have taken the section in this way and apply the elastic curve equation. EI into d2y by dx square is equal to mx, and mx is equal to Ra multiplied by x. This is the first one. Generally, in the Macaulay's method, we have taken the section or lines. like this. I can show this lines. This is the first one. So like this first line, then minus moment due to this UDL, that is 12 kilonewton acting over 4 meter. But we can take the section from the left support x distance. That's why this distance is 1 and this is x. That's why 12 into x minus 1 into x minus 1 by 2. That's why 12 into x minus 1 plus 1 square divided by 2. That is the moment due to the top UDL. Okay, this is the second section. So I have taken the another vertical line. Okay, but it is not necessary to show the lines. This is just for our understanding. Then the moment due to this load is in anti-clockwise direction. That's why minus. But moment due to this downward load in opposite direction, that's why it is plus clockwise direction. So 12 kilonewton per meter multiplied by this distance is 3 meter and this is x. That's why this UDL acting over x minus 3. So 12 into x minus 3 into x minus 3 divided by 2, that gives 12 into x minus 3 whole square divided by 2. This is the moment equation or elastic curve equation. Then we can see that this is the equation number 1. So this equation, integrate this equation and we get the, sorry, after integration we get the, just a minute. After integration we get the slope. So EI into dy by dx is equal to C1 is the constant of integration. 14.40 x is converted into, after integration, it is x square by 2 minus 12 x minus 1 square is converted into cube divided by 3 into 2, 6 plus 12 x minus 3 to the power 3 divided by 6. This is the equation number 2. Then again integrate with respect to x, we get the deflection. So third equation, EI into y is equal to C1x, constant of integration, into x plus C2 is the another constant of integration, plus 14.40 x cube by 6 minus 12 x minus 4 to the power 4 divided by 24, because 6 multiplied by 4 it is 24, plus 12 into x minus 3 to the power 4 divided by 24. So this is the equation number 3, which is related with the deflection equation. And we know that for cantilever at support, just a minute. Sorry. At support A, we know that the value of x is equal to L, that is 5 meter. So y is equal to 0. Okay. And similarly, at x is equal to again L, that is the total span 5 meter, dy by dx is also equal to 0. And after doing this, we get the value of C1 is equal to minus 1 by 80 and C2 and C2 x is equal to 3 meter. Okay. Okay. So C1 is equal to 1 by 18 and C2 is equal to, I think it is not clear. C1 is equal to 1 by 18. C1 is equal to 1 by 18. Just a minute. So EI into Y is equal to C1x plus C2 plus 14.40 x cube by 6 minus 12 x minus 1 to the power 4 divided by 24 plus 12 into x minus 3 to the power 4 divided by 24. This is equation number 3. Then apply the support condition. As we know that here there are support A where the slope is there, but the deflection is 0. Similarly, at support D, slope is there, but deflection is 0. Therefore, when I put x is equal to, section will be taken from left to right. That's why when I put x is equal to 0, y is also equal to 0. And similarly, second condition, when I have put x is equal to L meter, that means x reaches to 5 meter, y is equal to 0. Put this to equation condition and find out the C1 and C2. So in this way, when I have put x is equal to 0, y is equal to 0 in equation number 3, we get C2 is equal to 0. And when I have put x is equal to L, that is 5 meter, that is at support D, y is equal to 0. Put in the same equation number 3, we get the C1 is equal to 180. And after replacing the value of C1 and C2 by minus 180 and 0, we get the equation number 4 and 5. 4 is related with the slope and 5 is related with the deflection. Now in this problem, we can find out the deflection at C. That is at the 3 meter. Therefore, I have put x is equal to 3 meter, EI into dy by dx. That is this is the slope equation. So we can find out the slope at this point is equal to 131.20 divided by EI. This is related with the, not the slope, it's not deflection, it is slope. Okay. Similarly, when we can find out the deflection at C, again, this is equation number 5. Okay. This is equation number 5 of E. For deflection at C, again, I can put x is equal to 3 meter. So here at C, put x is equal to 3 meter and find out the deflection. For deflection, I can put here C2 is definitely 0, C1 is equal to 180. So here I have put x is equal to 3 meter, okay, plus C2 0, and then again this x to the power, that is 3 meter, x minus, so this is again 3 minus 1 to the power 4, and this is 12 into 3 minus 3, it is 0. That's why this term is vanished, and we get the deflection at C. In this way, we can solve the problem. So, thank you. Have a nice day. I hope you are getting idea about the unit number 1, which is related with the slope and deflection using the Macaulay method, that is the double integration method, moment area method, and the conjugate beam method. Thank you.